length of that map. You do that a couple more times, and you can get it for the length, the height, and the width, and then multiply all those together to get an actual volume, and you get the volume it would take to make that in a factor of cars. So you would have to take 2.1 times 10 to the 58 cars to make that map. That's 2.1 followed by 58 zeros. That's a big number. So that's just how many cars it would make. But let's talk about what's in cars. Cars have steel in them. It's kind of good. I don't want to get in a crash and have my car made of jello. Steel is a good thing to put in cars, but steel is 95% iron. Iron is a nice element. We can talk about that. So we're going to scale that. 95% of 770 is 730. So now we need to multiply that by our scale up factor we just got, which means we're going to need 1.5 times 10 to the 61 kilograms of iron to make that map. That's a big number. Alright, so problem. Galaxies don't weigh that much. A galaxy only weighs about 1.9 times 10 to the 43rd kilograms, which means it's going to take somewhere about 7.9 times 10 to the 17th galaxies just to make the same mass.
Nice.
So back in 1999, there's this thing called the Hubble Space Telescope. You took a picture of a patch of the sky in which it seemed that there was absolutely nothing. They just wanted to see what would happen if they pointed at this little tiny piece of sky about the size of Roosevelt's eye on a dime held at arm's length. That's what they were focusing on, and they left the shutter open for days and days, and what they found is that even the most blank parts of the sky are filled with galaxies, these things off to the right. Everything you see in that image is a galaxy. There's not a single star from our own galaxy polluting that image. That's all galaxies. So then what they did is they go, okay, well, there's this many galaxies in this part of the sky, multiply that across the entire sky, and we can estimate how many galaxies are in the entire universe. Turns out there's only 1.25 times 10 to the 11th. Who remembers the number from the last slide? 16. This means that to get that much mass alone, we will need 6.3 times 10 to the 6th universes.
Yeah.
As an astronomer, I work with the biggest units in the universe. I work on scales of galaxies, parsec, the biggest things you can think of. And when I came up with this question, I was not prepared to use units of universes. It did not happen. That's just to make the same mass. But there's one more problem. Galaxies aren't just made of pure iron. They're only 0.001% iron, which means we're going to need to multiply that last number by another factor of 1,000. So we will need 6.3 times 10 to the 9th universes to make that much iron. If you know that the big evil threat is that the spiral warriors are going to unleash their spiral power and it will eventually destroy the universe. Well, gee, I wonder why. Max destroying billions of universes to make their damn max. That's the real threat. So, will this one work? Well, we don't actually know that there are any parallel dimensions, so I am calling this one busted. Cowboy Bebop. A little bit better. All right. So there's an episode where they're doing deep space trucking, and this happens.
Oh yeah.
Like floating axe. I've been forgetting to ask. Is that going to work? No! That long it will work. Exactly. Hell no, who thought that up? I think you all actually know what happens from other things. Their heads explode, right? Well, it turns out back when they were first getting started with NASA trying to do all the Apollo programs, send humans up to space, they did a whole bunch of research on what would happen to somebody who just basically got shot out into space. There's two main effects you have to worry about. The first one's called explosive decompression, and the second one is what happens if you're in a pure vacuum. A lot of these effects overlap, so I'm just going to make one big long list. Bad. First off, you have severe abdominal pain. Whether or not you realize that you have a lot of gas dissolved in your blood, dissolved in your intestines, dissolved in your kidneys, your stomach, your lungs. There is a lot of gas in your body, and if you took high school chemistry, you probably remember that PV equals nRT thing, which means if the pressure goes down, the volume goes up. If you go into no pressure, the volume goes up a lot. and that's why your head explodes. Well, not quite. Fortunately, our body is strong enough to actually contain that pressure, but it's not going to be comfy. You also are obviously not going to be breathing, which means you're not going to be taking in oxygen, so you're going to undergo what's called hypoxia, which means you don't have any blood. As a result of that, you're going to turn blue. It's called cyanosis. Yeah. So as that gas expands, it's going to form nitrogen bubbles in your blood. If it gets to your brain, it can outright kill you. Back when they were building the Eads Bridge in St. Louis in the late 1800s, they were doing it in cisterns at the bottom of the river. And they'd bring them up in elevators real quick, and people go, I die. Actually, this is a serious thing. This was the first time they realized that there was actually something called decompression sickness. And that's a result of these bubbles forming in your blood, getting to your brain, getting to your heart, and mucking things up real good. Of course, even if that doesn't kill you, it can mess up your central nervous system really bad. That's not good. Oh, and if that's not bad enough, you might feel a little nauseous. Obviously, if you're expanding from gases, you're going to get swollen up. That can tear your tissue, especially soft tissue, eardrums, sinus tissue. And even if you survive the pain and don't pass out from that alone, it's going to take about 15 seconds for the blood from your heart to get to your brain, and after that you've got no more oxygen there, so you're going to pass out pretty quickly. All this came from a really fun paper to read called Rapid Explosive Decompression of Emergencies in Pressure-Suited Subjects. This was the most disturbing thing I think I've ever read. 100 pages of, man, you're screwed. Alright, but that's just what happened. So let's see what's going to happen to Spike. First off, in this paper they also had a whole bunch of studies where they basically had tests on 4 helpless little animals. I know, there were studies!
For your safety.
What they did, basically they put them in chambers, let all the air out real quick, and then see what happens. There's 2 things I really want you to pay attention to on this. First off, basically how quickly they did it, which is time. If they did it in almost 1 second, 0.6 seconds, the mortality rate was 0. That was nice. Kind of hurt, but the bunnies are okay. Meanwhile, the quicker you do it, going down to almost 1/1000th of a second, the mortality rate starts going up. That means the quicker that you let the air out, the more likely you're going to die. The question is, where is Spike on here? Another graph from this paper, a nice fun logarithmic graph. We need to figure out where Spike was on here. Basically, we got the area of the orifice, stop thinking dirtily. Orifice just means an opening. How large was the hole that the air was escaping? It was a nice circular shaped cockpit about 2 meters in diameter, so 2 pi r squared will give us the area of the orifice. He's somewhere about right here for our area. And the volume, again, it was a sphere, so I can estimate that. He's somewhere up here, put those 2 together, and his actual point is right about there. That means if you look at those diagonal lines, you can figure out how long it's going to take the air to get out, and it's so, close to that 1/1000th of a second. So where does that put him on our bunny table? Kind of puts him in the not so good zone. I actually plotted up all these things, and I couldn't get it to export for some reason, but it's a logarithmic graph. It put him in an 87% chance of mortality. That's not good. Either he doesn't know this, anime physics works differently, or he's just stupid. Well, so to summarize all this, actually no, let's go through this first. There's another thing that a lot of shows are going to show when people jump out into space. I know there's a Disney movie, I can never remember the name of it, but he jumps out and turns into a popsicle. You guys all seen that?
Yeah.
How is it? Well, there's 3 ways we can transfer heat. There's conduction, convection, and radiation. Conduction basically means if I come up and put my hand on your face, I'm really sweating right now because I'm in all this really heavy costume and it took most of it off, but I'm still really hot. So if I put my hand on your face, I would transfer heat from me to hopefully you're a little bit cooler. Direct contact transfers heat because the molecules in my hand are jittering, they pass that energy on. Another way is convection. I'm giving off heat to the air that's right next to me. The air goes up because it's hotter, it passes off the heat to the ceiling. When it gets up there, cools down, and it starts making these big currents. Have you ever boiled water? You've seen this? That's what boiling is. It's a convection current in your pot. It's hot at the bottom, carries the heat to the top, dumps it off, goes back down for another trip. That's another way you can get rid of heat. Or radiation. Basically, I'm giving off infrared radiation all the time. You'll probably feel it. A heat lamp does the same thing. Infrared radiation is another way to carry off heat. So let's see what of these would work for Spike. Conduction. Is he touching anything? No, he's in a vacuum. Wrong, not working. Next one, convection. Is there anything to move? No, he's in a vacuum.